Okay, very good. Yeah, Paul here has graciously agreed to give us a talk. So we're happy to have Paul here to tell us about tunnels and wells and scalar curvature. Please begin.
Okay, so there's a long history of tunnels and wells and how they interact with scalar curvature, starting with a construction of Gromov and Lawson and also Shane Yao at the same time, and they show that the impetus for what their construction, why they wanted it, was to show that if you have two manifolds that emit positive scalar curvature, their connected sum also carries a metric of positive scalar curvature. They can also get this to work for manifolds obtained under surgery, also admit positive scalar curvature. This construction was refined by Dodgewick, Basilio, and Sermani to give control over the volume and the diameter of the tunnel and maintain positive scalar curvature, but they do it on constant positive scalar curvature manifolds, and they maintain right positive scalar curvature, sectional curvature. And then recently more, it was refined by, and we replace sectional curvature, positive sectional curvature with positive scalar curvature. But then you want to ask the question, can tunnels be constructed, right? So under these constructions, you could have, you know, your scalar curvature on your manifold M could be bigger than, say, 7. But then once you construct your tunnel, all you get is that it's positive. So there could be a drop, right? We don't know. So there could be a drop. Who knows? So the question is, can tunnels be constructed with scalar curvature close to the initial scalar curvature to which we're going to attach the tunnel to? In relation to intrinsic flat limits, tunnels have been used to construct many different types of limits and to explore what can happen under a limiting process in the intrinsic flat sense. So they constructed short tunnels, Basilio, Dodgewick, and Sermani, to construct sewing manifolds. There'll be a picture in a second. And using these, they were able to construct a sequence of asymptotically flat manifolds with non-negative scalar curvature, empty boundary, and whose limit of the ADM mass is 0, and it converges in the pointed Gromov-Hausdorff and the pointed intrinsic flat sense to Euclidean space with a curve pulled to a point. So let me just draw what the limit space would look like, right? So it's going to look like Euclidean space, and then you'll have some weird wiggly wrinkled ball attached at a point. And so how do we see this? So this is a picture of one of the elements of the sequence that will have a limiting, that will limit to Euclidean space with a closed curve to points. What do you do? Well, you find a curve in your space. This is called the AJ0. And then along the curve, you center geodesic balls, small geodesic balls along the curve, and then you'll connect them with a tunnel. So kind of small, but right. So we want to connect. If I zoom in, now we can do this. Connect these with a tunnel, and we connect each of them with tunnel. And the tunnel, the point of the tunnel is that it will provide a shortcut, so that the diameter of this tubular neighborhood around our picked out curve ends up going to 0. And then if you do this carefully enough, you'll be able to get a limit that satisfies, get a sequence that satisfies these properties, and a limit that is not Euclidean space. So we see tunnels. If we allow tunnels can cause pathological limits we don't want, right? We would want a limit like this to converge to Euclidean space for stability of the positive mass. So somehow we need to think about what goes on with tunnels. Tunnels have also been used to construct other types of limits. So they've also been constructed to same thing. So same sewing manifold picture, So positive scalar curvature limit whose fails to have a generalized scalar curvature in the limit. So this picture's the same, and so what you end up getting is, I'll just draw a sphere, and we can pick a curve again in here. So I'll pick the equator. I'll pick a different color. I pick the equator, and then we again put some balls in here, and we connect them with short tunnels. And then we pull, then in the limit, this will go to a wrinkled sphere. So let's see, draw this, something like this. And if you calculate the right generalized scalar curvature at this point here, you'll fail your scalar curvature generalized. Let's just say this, generalized scalar is, well, goes to minus infinity at that point. And then also, Basilio, Cazares, and Sermani have used long tunnels, right? So these were short, thin tunnels, and now we can use long tunnels to construct a sequence of manifolds whose limit is not locally geodesic. So again, just to explain that, just example to say the tunnels cause problem. So how can we prevent tunnels? Well, we can require a uniform lower bound on min A, which is the area of the smallest closed minimal hypersurface in M. And how can we see this? Well, right, so if we have two parts of a manifold connected by a tunnel, right? So we have something over here happening, we have a tunnel going on, and attaches to another part of a manifold. Then we see that in here, we'll have a minimal surface. We'll have a minimal surface, and this sigma, let's call it, and the area of sigma will be small. And in all those examples above, right, we're taking tunnels, right, and we're shrinking them to like line segments, right? Line segments in a sense. And so we see that this area will go to 0. This area here, right, go to 0. And so we require a uniform lower bound on this min A will prevent tunnels from appearing. At least this seems hopeful in 3 dimensions. At least pathologies won't happen. So now we'll talk about our the other. Oops, went away. All right. So wells, right, was the other topic for the talk, right, and how do they relate to scalar curvature? So there was this sequence was first described by Hominin, and so what you have is a sphere with increasingly many thin wells attached to it, and in some sense, you know, we wanted to converge to the round sphere, right? So this is round spheres with many wells, and we want the limit to be, say, the round sphere. You could ask this, right? So I just picked this sphere topology because I had the picture, but you could picture this with any topology and ask the same question. We know that this limit will not converge in the Gromov-Hausdorff sense, and this is due to Gromov's compactness theorem, right? So we have, if all of these wells have depth, say 1, then we can fit geodesic balls around the tip of them of radius 1/4. And so we'll have in the limit increasingly many disjoint balls of radius 1/4, and this says that there is no convergent subsequence in Gromov-Hausdorff sense. So it needs a different sense to converge. These were first shown by Sermani and Wenger to converge in the intrinsic flat sense. So, right. Yes. And then Laxian showed that the sequence can maintain positive scalar curvature. So you can construct wells with positive scalar curvature, attach them to manifolds of positive scalar curvature, and take your limits in this sense and go. And so Lee and Zermani constructed this example in the setting of the positive mass theorem and the Penrose inequality. So I think we have a picture next, right? So how do they do this? So first, they take a rotationally symmetric. So yeah, let's just go through this picture quickly. So here they have a rotationally, the purple, I think it's purple or blue, rotationally symmetric manifold, and they have a sorry, lost my train there for a second. Right, and then they want to take a stripe in it, and that is what this lighter purple is here, and have it have positive sectional curvature. So there's right, just a stripe from a round sphere, and then we have this rotationally symmetric manifold that will be S dot flat. But now, since we have this stripe of positive scalar curvature, we can attach a well and obtain this picture. And so you could attach many wells all along this stripe of positive scalar curvature and have this problem where things don't converge in the Gromov-Hausdorff sense. But will converge in the intrinsic flat sense. Right, and so many examples of this sort have been constructed for manifolds of boundary, sequences of tori, but most recently, I think, no, I guess they came at the same time. Right, so we've constructed these examples and they converge in the volume above, distance below sense. And then you can also use wells to construct an example where the limit's not precompact. And this picture's a little different, so I have it here, right? So in this picture, we have that the wells persist in the limit, right? So you just add more and more thinner wells as the sequence goes on, so that in the limit, you have a collection of thin wells all converging kind of at one point. But so it won't be precompact because these have too many disjoint balls, again, at the tips of these wells. And so again, we want to ask this question. Can wells be constructed with scalar curvature close to the initial scalar curvature? And so our answer is yes. And here's the technical proposition of mine that lets you construct tunnels. There's analogous one for wells, but we'll just keep the one for tunnels here. Right, so we start with a Riemannian manifold with scalar curvature Rm. We pick a delta small enough, some J, and D will be the diameter of our tunnel, right? So this is what the D stands for, or about the diameter of the tunnel. If the scalar curvature is bounded below by kappa, so this kappa, we'll note, is just the real number, right? So it can be anything, right? There's no reason for it to be positive, anything. So this will allow gluing and keeping scalar curvature close, given any lower bound on scalar curvature. And it's local in the sense that we just need to pick two balls to which we will cut out of our manifold and then replace with a tunnel connecting the two boundaries. Right, and so the conclusions is that we construct a new manifold, Pn, by taking out, like I said, the two balls in our manifold M and replacing it with a tunnel, right, which is diffeomorphic to this cylinder. If you're careful with the construction, you're able to keep the scalar curvature the same. You drop only by an arbitrarily small amount. You get to pick your J. Outside of the tunnel, the metrics do not change. We only have a local change in metric near the tunnel. So so maybe I draw something. This will help. Right, so how am I picturing this, right? So this is our manifold M, and then we cut out two pieces, our balls. Right, these are our balls. And then we connect with a tunnel T. Right, and so we know that the tunnel status keeps scalar curvature close to the scalar curvature of the original lower bound, and outside the tunnel, right, outside the tunnel, metric does not change. Doesn't change. And lastly, we're able to control the diameter, which I'm missing something, so I want to say this. So we are also, diameter is lower bounded by D, and so diameter is controlled by D and D and delta, and the volume is controlled by this delta. Right, so then these two things will be helpful when we're trying to take limits of intrinsic flat convergences, because we need to know things about volumes and diameters to make sure. Does anyone have any questions so far? There's a lot of information on this slide.
So there's one thing I want to point out. For those of you, for Dimitri in particular, with the harmonic functions, I'd be curious if you, while you're watching this talk, if you could think what might happen to the harmonic functions when this is done. Because I've been really trying to imagine what happens to the harmonic functions, to your harmonic functions that you use in your mass formula when you add in things like tunnels and wells. What do the harmonic functions do in the wells? Because Paul Sweeney is going to present some pretty detailed explanation of how to make these guys. So maybe you at the same time can think of what happens to harmonic functions. Anyone who wants to. Thanks.
All right, so so this just says we're able to do this general Illmann construction and get a result, right? So we just have some manifold, usually closed manifold, let's just say. Then we're able to select, let's just pick a small region in here. And then in here, in the green, right, in the green, using the above for the well case, add many wells. Many wells, and then this will converge in the volume above, distance below sense. So just a quick word about why we would think that's true. Well, these wells, well, if you select your wells carefully, right? So we just have a bunch. Think about these all sitting in this green patch up there. The volume of this patch, right? The volume of the green is converging when the wells shrink to just the patch without the wells on them, because the wells will shrink and to lines, and if there's not too many of, well, if you add them correctly, you'll be able to get volumes converging back to the original one. And then the identity map, because you think about what we did here, right? We took a ball, a geodesic ball in our manifold, and we placed it with a well, right? And so this is so the metric here, right? The metric on this metric, new metric. Let me say this is, right? This will be G naught, and this is GJ. Pictorially, it's easy to see that GJ will be bounded below by G naught. And these are just the conditions you need for volume above, distance below. So you get convergence of these manifolds with a little, with once you convince yourselves that these two statements I made are true. And then next, right, we can also do the sewing manifolds of Zermani and Basilio with now keeping scalar curvature close to the scalar curvature of our original manifold, to which we're adding a bunch of tunnels to. And then we pull, we take limit, and then we get a pooled string space. These pictures I was drawing once we shrink the curves in the sewing manifolds to a point. All right. So now let's talk about how we can prove, how we can actually construct these tunnels or wells. And so, and sketch this, the proof of this proposition I had a few slides ago. So what do we do? So like I've been saying, right, we want the scalar curvature of the tunnel to be close to the scalar curvature of the geodesic ball. We want to control the diameter and the volume of the tunnel and the well. So just for simplicity, for formula wise, we'll consider the case when we're gluing to, say, a space of constant sectional curvature. But I'll make this comment. So if we have a ball, yeah, so let B be just a ball in some manifold. So B, a ball in, let's say, of radius delta in a manifold MG. Then the metric, so on the ball of radius delta, can be written in polar coordinates as like dr squared plus gr, and this gr is just a fact minus the round metric of radius 1 goes to 0 in the C2 sense. So basically all the formulas I'll write down, this is just to say, will also be true in the general setting where scalar curvature is just bounded below, but then there will be a small error, and the error can be controlled, and there's not much to worry about. So, right, we let this ball, let B be a geodesic ball in our space. Then we consider this cylinder, and it's in the cylinder that will construct our tunnel. So I'll draw some pictures in a second. I just want to get all the information for the setting out there, right? And so if rho is the geodesic radius from the center of our ball B to its boundary, then this strip of R cross rho is totally geodesic in the cylinder X, right, in X. And so we'll take a curve from the interval into the strip S that's living in X, and we'll define a hypersurface as all the points that are a certain distance from this curve gamma. So in a sense, you can think about this as rotating. So let me draw a picture. So right, so if this is S, right, so this is the this is R, this is the ball, right? So this axis represents the ball, and this is the total space X, right? And then so actually I want to write this differently. So, yeah, this is right. So this is S, and this is the rho direction. And so we draw some curve gamma, and then what sigma is the surface you get by rotating gamma around this R axis. So right, let's put it in quotes, the surface of revolution, right? So this is only really true in our specific setting. We have constant sectional curvature, but you're, again, for the thing I said before, you're close to, and you're morally a surface of revolution in the more general setting too. And so since this is our surface, the goal now is from gamma, if we construct a gamma, can we get control over the surface sigma, which will be our tunnel or well, right? And have it have desired properties, right? The scalar curvature, and control the diameter and the volume. The answer is yes, but let me tell you why and how. So, right, so let me draw again this picture, right? So I had it once, but right, so we need to keep this in our, so now I'll draw like, so we want gamma to be a tunnel. So what will this look like, right? So this again, it's S, this is the rho direction, this is the R direction. So this is in these coordinates, this is the T axis, and this is the R axis. And what we need is, right, we want gamma to look like this, right? Because when we rotate this around, rotate to get sigma, we'll have half a tunnel. This will produce, right? This should produce, right? This should produce. So this is what we're aiming for, a gamma that looks like this, right? Produce half the tunnel. Half a tunnel. And then you do the same construction on the other ball, and that gets half a tunnel, and you glue the two tunnels together. This is kind of the overall picture of what you do. So now let's construct a good gamma, basically. So I need to draw this picture again. Rho, R, E-axis, R-axis. Okay, and then, oh, I should have brought this all up. Sorry, here we go. Tunnel. All right, I just wanted to draw this picture and then explain the formula. So okay. Right, so in using the Gauss-Kadazi equations, we're able to write the scalar curvature of this hypersurface sigma in terms of using the ambient, what we know about the ambient curvatures of X cross, of X, right, which is our ball cross R, which is where gamma, where sigma lives, right? Sigma lives in here. So what we see is that we have two important things to notice from this formula, right? So this depends. First, we see if theta is 0, right? We start with, then we get RV, or the scalar curvature of the original scalar curvature of the ball, or the thing we want to attach to, right? And then so this means if we change theta a little bit, so we move off of the R axis, right? So this initial movement here, yellow is such a bad color. Right here, so I'll call this just the initial thing to sort of bend off, just to get off of the R axis. We have to lose a little bit, right, from this formula, because well, basically, right, so the bending off is theta, and this will dominate as a negative number, and so we'll drop a little bit. But the claim is you only drop, that's the only time you pay. You only pay to bend off of the R axis, and then once you do, you're able to keep things large. So that's what I wanted to say about this. Yeah. So somehow we want to maintain this closeness once we get off. So how do we do this? Right. So now we'll get into how we actually construct gamma. Now we have a picture in our mind and the things we have to control. So a curve in the plane, right? So we're thinking about this as happening in S, right? Right, in S, which is rho cross R. And gamma is completely controlled once you know it's geodesic curvature, right? And how do you get gamma from a geodesic curvature? Well, these are the formulas, right? Geodesic curvature gives you the angle, and then once you know the angle, you can calculate the R position and the T position, the height and the depth. And so we will, using these, we'll prescribe a K, right? So the goal is now, the goal is prescribe K of S in the right way. So we want to prescribe K of S in the right way. And so how we'll do this is the goal is we'll inductively define K and then do a smoothing procedure at the end. So let's see what we start. So the first thing we need to do is get off of this, right? I'll draw this picture again. This R axis. And what we'll do actually is this first turn will be a bit of a part. So this is all going to be summarized in some words after I click, but I just want to parts of a circle of radius 1. That will be so that's tangent to the R axis, to the R axis. So that's the initial thing we do. Just get off a little bit by saying, you know, K of S will equal 1. This is so right. So here, right, K of S equals 1. And then we're off. We're off in, and we can do better then. But this is how we start. So let's just summarize that in a few more words. So right. So using this, like I said, we'll do a piecewise. We'll construct them as piecewise circular arcs. In the first part, we choose to be a circle of radius 1, tangent to the R axis at some point delta naught. And then we choose, we let that curve go long enough, right? So that we only lose this 1/j that we chose at the beginning, right? We chose j at the beginning. Okay. And now we have one key lemma. So this is the one that lets us just win the game. But so right, if we have this delta naught small enough, so I'll draw the picture again. Right, so this is delta naught. And this is our gamma of S, right? And then S naught happens somewhere, right? We go along for some time. So this point here will be, we'll say, gamma of S naught. So we're asking, as long as we're not too far away from the t-axis, right? So that's what the first part, the delta naught says, which we can choose. It's fine. We can always make our tunnel thinner. Then if we can satisfy this inequality, we'll have that not only do we keep scalar curvature, we can make it, we could actually make it much larger, but will be larger than the initial scalar curvature. So again, I just want to emphasize that the only place we lose scalar curvature is between 0 and this S naught, right? When we have to actually get off of the R axis. Okay, and so now we're in a setting where we can choose. So now I guess maybe we can see what we want to do next, right? So we'll just choose our next, right? So K right now, right? K on 0 to S naught is 1. So now we want to choose on, say, S naught to some S1, K to be some other constant, so some constant. And what does that constant have to do? Well, it has to satisfy this inequality. And that's exactly what we'll do. I think the next slide I have this explaining this. Yes, so we will. This is exactly what we're doing. So right, right, so on, right, we chose on 0 to S naught, K to be 1. And now this is how we choose, first off, our next interval, S naught, S1, and our next constant K, right? So this is what will be K of S on this interval. So first is the length of the next segment, the next part of this interval is determined by the height of our curve at the previous point, right? So this, draw it again, right? This is gamma of S, which is equal to T R, right, of S. And this prevents gamma from crossing the t-axis. So that's why we have this requirement. And then this is chosen specifically so that we satisfy the lemma and we can keep our scalar curvature big. And then there's one last thing with that I haven't mentioned though, right? But to make a tunnel, I've always been drawing this picture, right? That we have somehow get a full bend, right? So this, we look at the theta again, right? Which is 0 here. Theta is the angle that the normal of the curve makes with the t-axis. And so this, right? Somehow we make a full, like a half turn, quarter turn, right? So we go from, and so I've been drawing with this, and the question is, can you do that, right? So maybe these requirements don't let theta get big enough that you make a full turn. And the answer is they don't. So we can actually show that our theta i's are increasing in I just by a few calculations. But this means, right, this means for some I, right, larger than an m, depending on, you know, theta naught, which depends on how much scalar curvature we want to lose. We get a full turn, right? So I'm just going to call that we get a full bend, I guess is the word I was looking for, full bend. And this is good, right? Because in our setting, we get a full bend. And here, this really, this will look like, this will be, oops, what's the word I'm looking for? Well, mean curvature is 0, so we'll be more amenable to glue onto another tunnel. So this is good. Right. So now let's draw the picture of everything we have so far. Right. So let's draw this gamma of S. Right, so gamma of S defined inductively. Right. So we have the initial bend. And then we have a few more, right? These are all piecewise circular arcs, and then we're done here, right? We stop. At some point, once we get our full bend. And now, so what we'll notice is this gamma of S is piecewise C infinity, and I think overall C1, so from just looking at the formulas used to define gamma of S. So now we need to smooth this out. And to smooth this out, we choose a good, we choose a bump function to a bump function, a transition function, a smooth transition function from this to here in the right way, and we can smooth it out. It's not hard to tell. And this only, again, you can check the formulas. These will satisfy the lemma saying that we keep scalar curvature large. So finally, right, so now we have 2 tunnels, right? Well, now we have something smooth, right? And now we need to glue them together. And so what we do is in the, well, right, so in the setting that we're in, it's pretty straightforward to glue, right? So if we're in, right, B cross R, which is equal to X, and this is a ball in constant sectional, then more or less we can just stick them right together because we know everything about what the metrics look like at this endpoint. Now, if this was, so now I want to make a comment about what happens if this is just, right, scalar curvature, lower bounded. And this comes, morally, this comes from the same idea that this is this, right, this will be a small disk. So let me draw it in now. This is the, right, this is the boundary, the surface here, right, that I just drew in is the boundary of a geodesic ball. In the original manifold with radius less than, so if this ball had radius delta, right, less than delta. And this is just to say we want to use that same idea, this idea that we know that these metrics get close to the standard one in C2. And using this fact, you're able to explicitly construct an interpolation between the metric here and then the metric on your other half tunnel coming from the other ball, right? So let me just draw again, right? So, and I'll draw this one in red. Right, so this one we can think of coming from a different, the other ball B cross R. And then these are close. Right, so the moral is they're close in C2, here and here, they're close to, sorry, this is round in C2. So they're close to each other. So you can make you can connect, you can make a short path between them. There's a short connection between them. But I can go into more details if people want. But, yeah. So then we have constructed our tunnel. And so using these tunnels, we can use them in the exact same way as before. So now, let me just pause here for a second, and then I'll make a few ending remarks if no one has any other questions. But yeah, so let me pause. I want to go back up and show go back to the proposition that says we can construct these tunnels. I don't want to move from this page and if someone had a question on it. Okay, so let me just pop back up. Here we go. So right, hopefully, right. Oh. So right, so now that we've constructed these tunnels, right, and we've preserved the scalar curvature, and all they were was local to the balls to which we were excising. I haven't mentioned the diameter thing, but this that is it's a calculation, so based on the formulas, but the volume is easy to see. So what we do is, right, so more or less you look like this inside B cross R, and so you can estimate it by the volume of this cylinder. That's just right, this is just the constant, right, this starts at delta naught, right? So you can estimate it by that cylinder that will go around the curve that you drew. And you'll end up getting exactly a volume upper bound like this. And now we can use these tunnels to construct all the examples that we had above without, and yes, all the examples we had above. All right, yeah, I think I'll end there. So thank you. I hope, everything was understandable. I feel, oh.
Thank you very much. Very nice talk, very clear. Thank you. Okay, now please, we need some questions. Any questions for Paul?